And what's next?
R23. 4 pi epsilon not R23.
Okay, so that is our electron-electron repulsion. Now, we have not yet included the relativistic effect of spin, or accounted for the Pauli principle, which we will do. You know, not all 4 electrons can have the same spin. We haven't done that yet, but we have written a complete non-relativistic Hamiltonian for lithium. We've got 9 partial derivatives, and we have 3 attraction terms in the electron nuclear attraction part of the potential, and we have 3 electron-electron repulsion terms. Now, let me show you the essence of the problem. And from lithium atom on to DNA, it never changes. It just gets worse. And the essence of the problem is circled in pink for us. We have terms with multiple coordinates. And they can't be separated. In other words, up until now, let's look at the Hamiltonian. Here, everything, all the coordinates separate out, don't they? We've got x1, x2, x3, y1, y2, y3, z1, z2. Everything separates out. With the electron nuclear attraction, we only have 1 coordinate associated with each term. But it is the electron-electron repulsion that absolutely kills us, because down in the denominator we have the coordinates of 2 electrons in this messy 1 over the square root of the difference squared thing. These don't separate out well at all. Now, God can solve it, but we can't. We can only approximate this at this point. We can't really solve it. Okay? Now, fortunately, computer programs are getting ever more sophisticated, so it's easier to solve this than it ever was. And by solve it, I mean to approximate it well, not solve it rigorously. But this is the problem right here. Essence of the problem. Because what this means is the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. You can see how hard it is to pull out coordinates 1 from coordinates 2 in this. I mean, where would you hope to begin? And people have been now working on this problem for the better part of 100 years. Okay, so multi-electron problems, we go from things we can solve to things we have no idea what to do with in one fell swoop, as soon as we get 2 or more electrons. Okay, so what do we do?
We approximate.
Approximate. There's no way out. We need to approximate. The most fruitful approximation and one that you have been taught since high school chemistry The most fruitful approximation is the orbital approximation. And you've heard about atomic and molecular orbitals ever since you began your study of chemistry, physics, and biology. This is by far and away the most fruitful, and it's not the only one, but it is the most fruitful one and the most widely encountered. I mean, you already know about sp-d and f orbitals, you know about sigma and pi bonds in organic chemistry. You've done that. So in the orbital approximation, we approximate electron-electron repulsion. In essence, we treat it as an average. So we average over the effects of the other electrons. And so what this amounts to is we approximate this term. And turn it into something that has only the coordinates of electrons 1, 2, and 3. So it's kind of like this. I'm sitting at this point, what on average are the other electrons doing? And the only coordinate I'm going to need in the end is this one. I'm going to just kind of average those all out. That's how it's done. And that works for this first course in P-Chem up to the most advanced graduate courses where they're doing these sophisticated computer simulations of DNA.
So
you're approximating electron-electron repulsion.
So I don't think I heard that right. So you approximate a small section and then assume...
You kind of say, what is electron 2 feeling on average from all the other electrons in the system?
Okay.
Okay?
So you try to stick to just one electron.
Yeah. See, you want a one electron problem where you can separate things.
Mm-hmm.
Now, why is that? Let's now look. Okay. If you've got H of R1, R2, R3, and that can be broken into H of R1 plus H of R2 plus H of R3. If this can be done. As an approximation. Then the total wave function can be set up to be a product of one-dimensional wave equations, or one particle, another particle, and another particle. And then the energy can be set up as in simple terms as the energies of 1, 2, and 3. So this is separation of variables. Now, as wonderful as this is only an approximation. And this is only an approximation. But it's a lot better than nothing, okay? So you can separate the problem, you can separate the wave function into a product, and you could do this as an approximation. Now, are you ready to see that you've been doing this all your life in chemistry? Okay. Let's take the electron configuration of lithium. Ground state lithium. 3 electrons. Are you ready for this? Okay. So here Professor Schrödinger's equation says we're going to get a state for electrons 1, 2, and 3. Where this will be psi 1s. So I'm saying I can separate this. I'm going to put 2 electrons in the 1s, and I'm going to put the 3rd electron in the 2s. That is the configuration. I'm going to graft in a spin. I'm going to have the coordinate electron 1 to have upspin, electron 2 to have downspin, and electron 3 to have upspin again. So here I'm just grafting in relativity via spin. So if you ask where it came from, I just put it there.
Okay.
Okay? Now, what do you write for the electron configuration of lithium? You write 1s 2, 2s 1. Okay, you say there's 2 electrons in the 1s, and there's 1 electron in the 2s. That's just shorthand notation for the 1s wave function with spin up for electron 1 times the 1 electron wave function for spin down, coordinates of electron 2, times 2s wave function spin up, coordinates of electron 3. And we'll put a map around this. All of this that I'm circling, this direct product here covers 1s squared. I've got one electron in with a spin up and one with a spin down. And then the 2s up is shown here. So little did you know, all your chemical and biological career, you have been writing, you have been using the orbital approximation of averaging the Coulomb potential and saying I can write my wave function as a product of 1 electron wave functions. And I call those 1 electron wave functions things like 1s, 2s, 2p, and so forth. Now, it gets even better. Let's look at details. Okay, this can really be written as the product of a radial function times an angular function. Radial function, angular function. Notice the coordinates are those of electron 1. But now let's do something. It turns out that the L quantum number goes like this. So this is the principal quantum number. The L is the orbital angular momentum quantum number. And so this is just a shorthand notation, what we used in general chemistry. We've got the N quantum number, and whether it's S, P, D, or F, we have the L quantum number. And if we wanted to get more specific, M sub L is our magnetic quantum number.
What do we call L again?
So our magnetic quantum number.
No, just like L.
Oh, that's M sub L.
But like the L though, like because the N is the principal.
Okay, this is the orbital angular momentum quantum number. L's quantum orbital angular momentum, magnetic quantum number, and then there is a spin term that we get append to the N, and this is S and M sub S. We could graft this on.
Are we involving that at all?
So we just add it at the end, and S S is always 1/2 or minus 1/2, and you know that plus 1/2 is up arrow and minus 1/2 is down arrow. Or up arrow can be alpha and down arrow beta. But what I really want you all to grasp is you have been using a product of one electron wave functions formalism to handle the electron configurations of atoms since the very beginning of your scientific careers. This has been embedded in your understanding of what these things are. And it is this approximation. And so I'm giving an example for a 1s orbital. What's the principal quantum number?
0. Oh, principal 1.
Oh, and it's PAL rather than PLE. I misspelled it. So the principal quantum number N1 equals 1. L1 therefore has to equal 0. And M sub L1 can only have the value 0. And S is always 1/2. I chose N sub S to be 1/2. So this shorthand doesn't give us all the quantum numbers, but it gives a lot. So isn't it interesting? 1s2, 2s1, we have organized the orbital approximation of quantum mechanics, and we've embedded a lot of the key quantum numbers. Very cool.
No, I was M sub S plus 1 half. You just picked it.
Yeah, I just said it's either going to be up or down. I picked up.
Okay.
You could have equally well picked down. Okay. Now, you might ask, what are the consequences of adding electron-electron repulsion going to multi-electron atoms? We're not even going to molecules yet, although once we've got atoms, molecules will soon follow. So, consequences of electron-electron repulsion. So people now have written sophisticated computer software to approximate these wave functions in various ways. And in a way, the computer is the ideal tool to do it because it's messy and there are all these interactions and keep track of it all, and we can just never do it on a piece of pencil and paper. I mean, it's bad enough for lithium. You can imagine what uranium would be, or even worse, DNA. So that there are approximations that can be made. Okay, now, what do we want to do next? Consequences of electron-electron repulsion. So let's keep it super simple. Let's go even simpler than lithium. Let's go to helium with only 2 electrons. The 2 electrons are Coulomb interacting with one another. The Coulomb force, Coulomb potential energy. And by the way, just a verbal comment, very important. The Coulomb force between 2 charges is 1/4πε0 r squared between the forces. But if you integrate that and convert it into a potential, it's 1/r rather than 1/r squared. Okay, so, and we got it right in our earlier notes. That's really important. Okay, so now we're going to look at the s orbitals, the p orbitals, the d orbitals, the f orbitals, and the g orbitals of not of a 2 electron atom, not hydrogen atom, but helium. So here's the 1s here. Here's the 2s here. And now we see something absolutely amazing. And this makes the whole periodic table, and it makes chemistry as we know it. For atomic hydrogen, all you care about is the principal quantum number, because the energy doesn't depend on the L quantum number. In multi-electron atoms, you have this. The sp degeneracy that you found in atomic hydrogen is lifted when you go to helium. And so now we're going to go 3s (3p) and 3d. Okay. Now, are you ready for the center part of the periodic table? See, quantum mechanics is not without consequences, because now we go, let's say, to the 4s and the 4p, but that might slip under the 3d, or the s might slip under there. But what happens if this 4s, or the 3d is under the 4s? Then we have to put in 10 elements in the periodic table where we're feeling the 3d before the 4s. So we get the whole transition block of the periodic table. Because now the energies E don't depend on just N. So this is hydrogen. Energies depend only on the principal quantum number. In helium and upward, the energies depend on N and L. And that changes everything, and it totally changes the periodic table, allowing the F block elements, the lanthanides and the actinides, and the D block elements, the transition metals, to be interspersed in here. Pretty amazing stuff, if you ask me. I mean, absolutely incredible. Okay? So we lift the degeneracy of hydrogen, where we don't care whether it's an sp, d, or an f, as long as we know the principal quantum number. Now, it matters. Okay? Now, let's take a look at page 362 of our textbook. See page 362. And in particular, I want to look at key equations. This is on our atomic structure and spectra chapter. Okay, now, they talk about everything we have, the spectral lines of a hydrogen atom, the wave function of a hydrogen atom. We've done all that. We solved it analytically. The energies of hydrogen atoms, and you did a P-Chem lab where you absolutely drilled Rydberg's constant to the number of significant figures our instrument would record. Okay? Now, look at the term that says the orbital approximation. And it says the one wave function, the multi-electron wave function, is the sum, or this product, sorry, product and that it is this is the orbital approximation from which all of this comes, and which is embedded so deeply in your understanding that you can't really think of chemistry or biochemistry or molecular biology without thinking about orbitals. But it comes from making an approximation to the quantum mechanics that we absolutely have to make to get anywhere. Okay. Now we shift gears from a more quantitative to a more qualitative thing. And we're going to learn now how to account for the bewildering plethora of atomic terms and states of molecules. I mean, it's a mess if we don't bring some order to it. So, okay, it's a fact there are high degeneracies, and I'll carefully specify what the word degeneracies means. There are high degeneracies in the energy, let's see, in the quantum wave functions of multi-electron atoms. Now,
So they're all just in the same energy level?
yeah, so degeneracy means, in our case, it doesn't mean you're wrapped around a street light with your head in the gutter outside of a bar at 2 in the morning. That's not what it means. What it does mean is psi A and psi B are degenerate if EA equals EB. So different wave functions that have the same energy are degenerate wave functions, okay? And what we're going to find out in atoms, and we can find this out through spectroscopy, combined with theory, is that there are a lot of quantum states of atoms that have the same energy, but they have a different combination of quantum numbers. They're different states, okay? So we need a way to collect, identify, and group degenerate sets of states together. In other words, if A and B have the same energy, they have some relationships in common, and we want to group them together and we want to talk about them in groups. So for example, we say all the English majors on campus don't know what hard work is. You know, bio majors don't have any idea what calculus is. Physics majors can't handle the complexity of DNA. You know, I mean, you know, the standard insults reflect some of the challenges of grouping groups together. So we want to bring together quantum states that have the same energy. We'll find typically that they have some of their quantum numbers the same and others different. And we do this kind of as a matter of, help, we've got so much going on, maybe we should group them together by energy. Okay. All right. So, for multi-electron atoms, we need to be able to add together angular momentum magnetic quantum number and okay. So for one electron, we can have an L value, an M sub L value, an S value, and an M sub S value. S will always be 1/2, little s. M sub S will be 1/2 or minus 1/2. M sub L can go from minus L to minus L plus 1 all the way up to plus L. And then L can take on the values 1, 2, 3, up to n minus 1. So that's why you can only have a 1s, because the L quantum number has to be 1 down from the N quantum number. Okay, but this is only for one electron. Now we need to sum over to multiple electrons. Okay, so the whole process by which we do this is to create what are called term symbols. And term symbols represent groupings of wave functions that have the same energy. So we're going to find a whole bunch of degenerate sets of wave functions, and we're going to rank the sets in order of energy. Like this group of degenerate wave functions has energy levels that are higher than this group, that are higher than this group. it's a wonderful way to do it. You see that? Because, and there might be 20 wave functions in one, 10 in the other. It's a wonderful way to get ourselves organized in a multi-electron atom. Okay? Now, let's comment just a little bit. This is presented to us starting on page, let me read this, 357 on. And do I like the way the book does it? The answer is no, they don't really tell you how to do it. And they just kind of summarize the results. And my molecular spectroscopy book doesn't really tell you how to do it. So that, my friends, will have to wait till Thursday. But let's just make one comment. We're going to be adding angular momenta. And we'll find the basis for handling all these complex atomic systems. And from this, we'll shed some insight into molecular systems as well. So we're going to go way beyond the book with our term symbols. We're going to go way beyond the book with the formalism for adding angular momentum. And we're going to show you a way to draw complicated orbitals as well for hydrogen, or even, for that matter, multi-electron atoms. So some really cool stuff is coming up that will be more intuitive and less hardcore mathematical. In the meanwhile, I want you to be compiling your comparison of all these quantum systems that we had on the board at the beginning of the period. Okay, let me stop for a moment, see if there's any questions that this went over your head. I wouldn't be surprised. So we'll take another crack at it. It's absolutely lovely stuff. And you will feel totally empowered once you learn how to do these term symbols. And you can do term symbols for anything. You'll be just absolutely blown away. All right?
Alrighty.